Okay, this is Ms. Hall with Capital High School Science, and this video lesson is about CERs, and I'm hoping that most of you have heard about CERs at least in your previous science classes. So this should serve as a good review. I'm giving you some examples as we go through it. And I want to start with what is science. A lot of people think that science is just a body of knowledge. It's just the information in a textbook or information you can find online. It's already there. And I disagree with that. And part of the reason is if you have that view of science, that information becomes outdated pretty quickly. Science is very dynamic. As scientists carry out more investigations, as our technology improves, many of our theories end up changing slightly to encompass some new information. So to me, science is more about a way of thinking or knowing, and really the process in trying to find out more about the world around us. So we may never know everything, and that's fine. It's really the process of getting there that is science. Part of this process is known as the scientific method. So you may have been taught the scientific method in previous courses. Prefer the term scientific process because that's really what it is. And understand you don't have to go in this order. You could make your observations, you could do an investigation, it might not work. You may have to go back here. Maybe you don't even like the question anymore. So again, this is not a prescribed pathway. But going through this, typically, the scientific method or process would look like this. You have observations made about the natural world around you. Scientists would then hopefully ask questions. They're pretty inquisitive in nature or as part of their nature. And those questions might lead to investigations. So in a science class, you might be posed a question by your teacher, or maybe you come up with your own question, and that might lead to an investigation. And ideally, your investigations are controlled if you can. You have your independent and dependent variables. And again, typically in physical science classes, that's what they would look like. And if you have a good investigation, you get some evidence. That's your data. That's your quantitative and qualitative data. So quantitative data sounds like quantity, so it's numbers, masses, volumes, lengths, anything that involves numbers would be quantitative data. And then you also have qualitative data. So every lab, you should be recording qualitative data, quality. These are anything else that you could write down your observations using your five senses that don't involve numbers. So color, texture, smell. Are you seeing something kind of bubble? Those would be qualitative observations. So the quality of your evidence, of your data, depends highly on your investigation. So how good of a setup your investigation is. So let's assume you have good evidence, you have some solid data, then you try to make sense of it. The whole goal, again, is to go back and answer that question. So you're trying to make sense of it, see if you can make some explanations to help you answer your question, about these observations and some phenomenon in our natural world. All right, when we're talking about CERs, we're going to be living in this place. So we're going to be focusing on analyzing the evidence and trying to make sense of it, trying to explain what's going on and how that evidence hopefully enables us to answer the question. So this is what we're going to be looking at. So again, this is what I'm thinking through, how I think of this. You have your evidence, you have your data. You have to try to process that data. You have to think through it, maybe mathematically manipulate it to see if you can answer that question. And then just the data doesn't do much. You should be going through and use other scientific knowledge or understanding, so laws, hypotheses, or not hypotheses, theories, definitions, to tie that back to your question. So your reasoning is basically using all this information, the evidence, the sense making, previous scientific knowledge to answer that question in a meaningful way. You're developing an argument. You need to have as much support behind the argument, behind your claim as possible. All right, so we're going to kind of go through this process with an example. You'd start with a question. So again, a lot of times it's going to be proposed by a teacher, or it could just be based upon your observations if you have a more open-ended investigation. So let's say it was proposed by your teacher. This is the question you need to answer. Is air matter? So the next step would be an experiment. And again, you try to develop a controlled experiment that allows for the testing of just one variable at a time. Hopefully, you have good data, and then you can start thinking through your CER. So if you have your data, if you've processed it to the extent that you need to, now you can go to your CER. So your claim is the C of CER. This is the answer to your question. And depending upon your assignment, if it can be extensive or it can be pretty short. So again, our question was, is error matter? Your claim might simply be, yes, errors matter. However, if you're doing an actual conclusion, a CER type conclusion, you want to have a little bit of background information in there. So with ours, it'd be like, by conducting an experiment involving, you'll see I do 2 balloons, or the same balloon, one blown up with air, one without air, and finding the mass difference, we found that errors matter. So you do want to give a brief description of your methodology in your claim, in that introduction, but very clearly state what you found out, what your decision is based upon your investigation and based upon your data. So evidence. Evidence is, again, the quantitative. So remember, quantity, any numerical piece of data, and qualitative data from your investigation. So you want to include high data, low data, and any relevant processing of data, typically. Not always, it depends upon the question, it depends upon the investigation. But typically you'd like to see the high data, the low data, the mins, the max, from a specific trial, and then you would want to share the average differences. In the case of my investigation, could be a product, just depends again upon how you need to process that data to effectively answer the question. Don't do extra processing if it doesn't have anything to do with your question. So it needs to stay focused on achieving that specific objective, answering your question. So in this investigation, this example is error matter. I quickly described a balloon, and I found the mass of the empty balloon, the uninflated balloon, and it was 2.80 grams. And I did take into account the mass of the weighboat. I tared it, I zeroed it, so this is just the mass of the balloon. Then I blew it up, and that new mass, same weighboat, also take into account, is 2.96 grams. So there's my data. Now, I did not do 3 trials. I should have, but this is just for an example, a simple example of a CER. Okay, so I would also record some qualitative data. The balloon is yellow, it's made of latex, it's approximately these dimensions. That it definitely expanded in volume. I'd give a description of its shape and texture. All of that could be essential. So you want to record everything when you do an investigation that you're noticing, that you're observing, because you may include it in your CER, you may not, but you want it there in case you find that it could be relevant. Okay, so here would be my evidence. The mass of the empty balloon, my E in my CER, I should say, because you'd probably have a data table up above. And you would say the mass of the empty balloon was 2.80 grams. So that's my low value. After filling up the same balloon with Miss Hall's breath, the mass rose to 2.96 grams. And then this shows an increase in mass of 0.16 grams. I am not analyzing anything. I am just simply stating the key pieces of evidence. Here's what we do not want to see. I see this a lot. Please refer to the data table above to find the evidence or to show the data. That is not what we do in a CER. CER, you are pulling out the key pieces of data that's important and stating it in a very meaningful, impactful way. You don't include all your data. You just pull out what you think the most important piece of data or pieces of data are to support your claim. So in this case, I only have this data. That's all I did. But it is significant. It helps me answer my question. Okay, moving on to the reasoning. So the reasoning is a logical connection between your claim and your evidence. So remember, my claim is, yes, errors matter, and my evidence was that change in mass. You want to make sure you use scientific principles to justify your claim based upon the evidence. Okay, so this is where you pull in scientific definitions, laws, theories, principles. And a big hint, typically in a science class, is going to be related to the content in which you're covering at that point in time. So you use outside resources. Make sure you cite them. Make sure you are not plagiarizing, but use them. And here's a critical thing. This is the hardest part. The reasoning is the most difficult part in CERs that I see with students. It is not simply just restating the evidence in different ways. You've already done this. This is tying it all together. So this is tying your evidence to your claim. So how does that evidence support it? So in my example of the balloon, here would be my reasoning part of it. The increase in mass supports my claim that airs matter because matter is anything that has mass and volume. So that's important. We need to know what in the world does mass have to do with matter. And then I'm citing my source. We saw that when more air was added to the inside of the balloon by blowing it up, the mass increased by 0.16 grams. Thus, adding the air from Miss Hall's lungs added matter to the balloon. Also, the balloon took up more physical space. Visual or qualitative observations could be put here after being filled by air. Thus, the balloon's volume increased because matter or air was added to the balloon. Okay, so I'm tying in the definition of matter. It's something that has mass and has volume. And then I'm doing it in a meaningful way. I'm bringing in my key pieces of evidence and I'm going back and tying it to the claim. So notice I did not restate all my evidence. That is not essential. I already said it. I am just supporting what I already said and tying those pieces together. So you'd want to go back to my previous slides, the claim slide, the evidence slide, and the reasoning, and all those examples would come together to be one big final paragraph, one big conclusion.